Hi, welcome to Signal Path. In this episode, we're going to take a look at another repair video. This is an Agilent N4901B. This is a 13.5 gigabit per second serial BERT. BERT is, of course, a bit error rate tester. Now, 13.5 gigabit per second may not sound much these days because even for backplane applications, we're looking at 100 gigabit per second and even over that, and optics even more so. So it's really not that fast by today's standard, but when this thing was new, it would have cost a fortune. And even now at 13.5 gigabit per second, for a lot of applications, for memory interfaces and CPU and I/O interfaces, for a lot of parallel interface application, this is still very good. Now this has option 100, meaning that it has the pattern generator and the error detector built into it, which is fantastic, meaning that it's really, really expensive. And of course, you can see that there is no expense spared in the design of these things. Even though it operates at 13.5 gigabit per second, all the data and clock I/Os are V connectors. So just the cables and whatever you need to terminate into these is going to be pretty expensive just to get it up and running. Now this one has absolutely no sign of life, but its capabilities are incredible. It can do advanced modulation of the jitter. It can do error, of course, detection. It can inject a particular pattern of error. It can do full eye diagram, bathtub, curve traces, sensitivity measurements, you name it. It can do whatever you want. Really advanced. It's actually huge. This is a big, big instrument. It weighs a ton. So the fact that it has no life in it, I'm hoping it is just a power supply. And the power supply in these units are really complicated. So that itself would have to be analyzed quite carefully. But having said that, I think this runs Windows, and we'll see what happens when we open it. I hope nothing else is bad with this, because if one of these channels is dead, basically the whole thing is kind of useless, and this is going to be very difficult to fix because these are going to terminate into custom ASICs right behind the interface here. So we'll take a look. Tons of cool things in here for sure, but I'm really eager to see if we can fix it. That would be a really fun thing, because if I can fix it, then I can show you a ton of experiment that we can do with this. I have a lot of instruments in the lab where we can put 13.5 gigabit per second data through it. We can look at the scope, some of the oscilloscopes that I have that they can do different kinds of analysis on the eye diagram. That would be pretty interesting. I have retimers and backplane boards and amplifiers, tons of stuff we can take a look and see what happens to the ISI and errors and so on. So let's go and open it up, see what's inside. And here's the look inside the unit. This thing is absolutely massive. Of course, I particularly like their airflow solution here. This is some compressed styrofoam that they're using for a big, big fan in the middle over there. And this is actually made in Germany. And obviously it's going to be good. The core BERT is underneath here with all the front connectors here. So that's its own unit that interfaces somehow to this motherboard over here. That's a floppy. That's the front screen over there. Just a basic motherboard, some kind of an Intel processor there, the North bridge over here. We have DRAM memory. This is probably to the hard drive or to the interface to the BERT. And these are just a USB and GPIB interface. Really nothing unusual. That's just a PC. Now underneath there, underneath here is where the power supply is. Now I can't access it from here. I think it's going to be accessed from the back of the unit. And there's some power distribution network over here. So that I'm curious what's going on with that. There's our CAT scan. Pooch, what are your thoughts? Doesn't seem to care too much about this particular instrument. He's not into BERTs, aren't you, Pooch? So yeah, so let's go ahead and take a look, see if we can get the hard drive, or I should say the power supply out, which is underneath everything, but I think it can be accessed. So let's go and see what we can find. Well, how is that for power distribution? This thing has an absolutely massive power supply, which may have failed. And you can see here the back of the chassis that holds, of course, all the BERT parts. And there's a whole bunch of components already even in the back of the motherboard. So there's a ton of stuff is going to be, we have to take a look at. Now, these are all the power cables coming out of this power supply. This power supply has 5 modules in it, 3.3 volts, 12 volts, 12 volts, 24 volts, and 5.2 volts and 5 volts for different logics and buses and power supplies, drivers, and so on and on. This thing definitely has silicon and non-silicon parts in it. Few connectors connect the power supply to the chassis, so it's actually quite serviceable. It's obviously intended that the Lambda power supply can be removed. So you may ask yourself, why don't I check the power supply problem on the board itself? Now this is the area where the power supply connects. You can see two massive connectors, and here's the control of the power supply. This is B, this is A. I already labeled them on the supply itself. Now all the power supply voltages are actually written on the motherboard, and you can read them, all different ones, and each of them is individually fused, which is of course high performance good equipment will always do that to protect the power supply and protect the instrument from cascade failure. So we can go ahead and actually measure every one of those fuses just to make sure that something didn't go horribly wrong inside the chassis and cause the problem on the power supply. We're still not 100% sure if it's the power supply. It may very well be that the control signal, for example, that's supposed to trigger the power supply to turn on is not doing what it's supposed to do, and I have no idea which wire that would even be. So we have to go and see if we can figure it out once we analyze the power supply unit itself. But nonetheless, I can go ahead and check each of these fuses individually with my multimeter. And here's the first one. I hope you can hear that. So that one's okay. This one's okay. This one's okay. That one's okay. That's okay. And that's fine. Also fine. Also fine. Also fine. So the fuses all seem to be okay. So I'm not going to worry about that too much. Let's see if we can get the power supply to even start. If we can do that, then we can turn our attention to this. So let's go and take the power supply apart. I'm really eager to see what's inside the Lambda power supply. These TDK-Lambda supplies are amazing. This is a very good brand. So I like to see what's in it. And here is the power supply. It is enormous. And this power supply is customizable. You can put different modules in it. This one is fully populated, as you can tell by all the different voltages that are coming out of it. A lot of control circuitry in there. And I can do a quick search on the internet, see if there's any information about it. I doubt that these things are kind of protected in terms of schematic and so on. We're going to have to open it up and take a look. We can just work our way in from the AC signal and see what happens. And if we can find the standby voltages, it's unlikely that all the modules have failed. It may very well be that the front end is bad, which would make it a little bit easier to fix. But first, we're going to do a little bit of reverse engineering, a little bit of investigation before we do anything. And here is the inside of the power supply. And as expected, it is compact with a lot of different PCBs vertical, horizontally mounted. They're trying to save as much space as possible. So the input line comes over here. You can see the input filtering. This is the main part of the power supply where you have the rectifier voltages being stored here with a DC-DC converter portion here. And then some voltages are generated, passed onto this bank. And these banks are actually connected with a ribbon cable, which you cannot see, which is quite interesting in itself. And the rectifier is right down there. And there's a fuse right down here. And interestingly enough, that fuse, you can see I'm in continuity, and that fuse is dead. Now, of course, you don't want to just go ahead and replace the fuse because we have to find out why the fuse has died. And the fuse has protected, luckily, whatever that is the problem. That's why there's absolutely no sign of life, is because the AC line is just not getting in. So I'm going to try and remove all of this and see if we can reduce this power supply as much as possible to its fundamental building blocks, which is the main front end, rectifier, and DC-DC converter portion, getting rid of all of these and finding out what has caused the fuse to die. The absolute luckiest thing we can have is a very simple front-end failure, and of course the most complicated would be something deep within the switching power supply itself. But it still needs to be disassembled further because I have no access to the fuse even if I wanted to remove it. So it's not socketed, unfortunately. That's quite annoying. So it's really fascinating to see how TDK-Lambda has solved the problem of making a completely modular power supply. It's really cool to take it apart and take a look at it. So the reason I say that is because this power supply, as I mentioned, is completely configurable at the time you order it. You can put any module in here, create any voltages you want, put them in parallel, put them in series. Basically, it is completely up to the customer, which means that when you order it, they're going to build it to order. That's why the Vega 650 series is basically a completely customizable power supply design. So how do they do that? Well, it turns out that what they do is they keep the primary side of the power supply essentially constant, at least as far as I can tell. It is constant. So it's got the rectifier, the filter, the switching side, and the capacitors, and a whole bunch of other protection circuitry are here and there, the first side. And then there's some feedback voltages for protection, again, to turn things off if there's something wrong. But the transformer primary side is driven with this connector, which means that they can plug in a transformer in here and create primary to secondary connection. But then you ask, well, what about the transformer? If these modules are all customizable, how do they do it? How do they deal with the primary secondary connection of the transformer itself? Well, even that is completely customizable, which is really interesting. So here's the little module. The actual transformer is built inside here. I've taken it apart. Here's the primary side of the transformer. You can see it's made of much thicker cable, and you can have as many turns basically as you want. In this particular case, we've got two discs which are in series, driven by this connector right here, which connects to this connector over here. So the primary side is made of this. Now the secondary side is made of ribbon cables with discs of copper on them. Basically, it's basically ribbon cables with very thick copper, which you can bunch up together and sandwich between the secondary, and then primary like this. So then that way you have actually coupling, magnetic coupling between the two of them. And in order to maintain that and confine that, they have a perfectly machined piece of ferromagnetic material which sits in the middle, and these guys just slide into this position here, and then this couples on the other side, clamps down, and there is your modular configurable transformer. So they make that on the fly. Depending on what modules you put, they just clamp it down together, clamp it, and there it is, which is really quite incredible. So I really like this design. It means that you can basically buy any Vega 650 power supply and salvage parts out of it, which is what I think I'm going to do. So the very first thing we can try is we can, of course, bypass the fuse on this and find out why the fuse is burning up, and find out if there is a problem on the primary and where that problem is. So let's go ahead and set that up. I'm going to use my isolation transformer at much lower voltage. We can slowly crank that up and see if we see any issues. Okay, let's do some measurements. And again, here is the benefit of an isolation transformer. I can step that down and figure out what's happening to all the voltages. So here's the neutral, and the live is connected to the other side of the fuse. Let's go ahead and measure that. Again, this is completely safe because I'm using a very low voltage. So let's go ahead and try that out. Oops, that's not what I wanted to do. Let's plug this guy back in here again. So here's our neutral, and here is the live line. What do we see? So we have about 12.8 volt AC, which is what I have set my isolation transformer to provide. Now I expect that to be rectified and filtered by the front-end rectifier and stored on the capacitor. We can go ahead and measure that to make sure that's the case. I think this is negative. And what do we see? We see 16.4 volt DC and no AC voltage, which is what we would expect to see in this case. That's correct. Now let's go ahead and measure the transformer. Now the transformer right now should not see any voltage on it. But if I go ahead and measure that, you can see that I see the entire DC voltage directly appearing across this, which is of course not a good thing. It means that there is potentially a short between the capacitors and the transformer, meaning that it is possible for one of the switching transistors to have been completely shorted and therefore creating a DC path. And a DC path from the capacitors to the transformer would appear as a short circuit at DC, and that would instantly blow the fuse. We can verify by disconnecting this completely, get rid of this, and we can go ahead to measure resistance, and we can go ahead so we can see continuity. I'm going to touch one side of this capacitor and go to the transformer. You can see I have a complete short circuit to both sides, and if I go to the other one, I see a complete short circuit on one side, and on the other side there is complete short circuit. So these two are completely connected, and the other two are completely connected. And remember, these capacitors are large, so if you connect across them, you're gonna see that. But as soon as if you don't see 0 ohm, means you're charging the capacitor. So we can try again. That's a short circuit that's not charging the capacitor, and the other side, a short circuit not charging the capacitor. So that means that there is something gone horribly wrong. Well, what do we do about that? Well, there's a couple of things we can do. We can trace this out, and if you trace this out, you will see that inside of this module, where the transistors are, all the way in there, the switching devices are in there, so definitely something is dead. Now, in order to take this off, I have to unsolder all of these and figure out which one is dead and find the replacement, or I can do something a little bit different. Well, check this out. I just went on eBay and I searched for the absolute cheapest TD-Lambda Vega 650 power supply I could find, and well, I found this one. And I made sure that its primary configurations are essentially similar. Now, what was important is this side, that the primary option has at least the EW lettering on it, which it does. You can see in both of them. Now, this one has a primary auxiliary voltage of 5 volts, and this one has the primary auxiliary voltage of 13.5. So the primary side circuitry is not suitable as it is to be used instead in here. We have to open this up, find out if the primary option card is interchangeable between these models. Now, this is supposed to be a working power supply. I haven't tested it, but we can easily find out once we open it up. It's a very nice power supply. It's clean. You can see its configuration is completely different. It's completely configured differently in terms of the modules that are in there. It has a 5.2 volt 95 amp delivery, 3.4 volt 35 amp delivery, whereas this one has many other power supplies. So the secondary sides are completely different, and that's okay. We don't need them anyway. We need just the primary side. So let's go ahead and crack this one open and find out what's going on in there and see if we can do some kind of a heart transplant between those two. Well, check it out. It's very nice. It's a very clean unit. This one doesn't have a fan, so the fan connector is not occupied. But in terms of circuitry, they're essentially identical. You can see as far as I can tell. I just opened it, but there might be some minor differences between them. Colors of the capacitors are different, probably from a different batch, but everything else looks about the same. So we can go ahead and take this one completely apart and extract the module we want and see if it works. Okay, well, here it is all back together. We are using the new primary side. We're using the old auxiliary board, and all the old modules, everything's wired up as it was originally, except for the fan. Everything's powered off, nothing's connected right now. That's why I'm poking my finger in there. So let's go ahead and turn on 112 volts to it. Let's see, it's a moment of truth. And oh, okay, well, I heard some relay click. It's drawing about, let's see, about 90 milliamps from 115 volts. And that's, I don't know what the power factor of that is. But let's see if we get auxiliary 5 volts out of this bad boy now. Let's see, do we have auxiliary 5 volts? Ah, look at that. That is a good sign. So if the auxiliary 5 volt is there, this is now compatible with the BERT once again. I'm going to put the top cover, put it back in the BERT, and see if the BERT turns on. It's really exciting. All right, here we are. I put the power supply back, and you can see my reflection. Let's go ahead and give this guy a try. And oh, that's a good sign. It made a really weird noise when it started, but other than that, it seems okay. Let's see what's going on. No pooch. Sorry, pooch. You can't get in there. There are fans spinning. Okay. Interesting. Let me see. Press enter here. Okay. Well, it seems to be okay. There it is. Windows XP. It's going to boot into Windows XP, which is what is supposed to be installed on it. Now, this is going to go through a whole bunch of stuff. Obviously, it's going to boot into the operating system. And once it's in the operating system, it's going to try and bring up the BERT software. So it's going to take a little bit of time. I'm going to wait and see if it actually comes up correctly. Okay, it's still booting. We got CAT scan going on. He's making sure everything's in order. So a funny thing is that there are about 6, actually 8, wait a second, 2, 4, so no, 6 V termination and 1, 2, 3, 4, 5, 6 SMA termination. The cost of these 50 ohm termination, especially the V ones, the 1.85 millimeter ones, is much more than the cost of what I paid for this instrument, which is kind of funny when you think about it. So the firmware is still booting up. We'll wait a little bit longer. Oh, okay, the lights blink. That is fantastic. There we go. That's a good sign. The software's up. Uh-oh. What does that say? Delay control protection. Input signal at the delay control input is out of hardware specification. Well, that's not good. It seems to be talking about this, but I have terminated it into 50 ohms, so it shouldn't be receiving anything. Ooh, I don't have a good feeling about this. Well, let's go and see what's going on. So no matter what I do, I'm not able to clear this error, unfortunately. And even when I disable the delay control input, I still get the error. So you can see I can just get rid of that glare here. So even if I disable it, it keeps coming back. Of course, disable is done through here. And you can see no matter what, I always get this. So what is happening here is that we have an input that is delay control in, and this input is intended for jitter tolerance testing. So you put in a particular type of signal in here. It could be a white Gaussian noise, it could be triangular, sinusoidal, and it will apply that to the jitter of the eye diagram, the data pattern that's coming out of the data outputs. And that allows you to stress test a clock and data recovery system that follows this and then extract a jitter tolerance plot out of it. So the delay control input is a critical and important part of bit error rate testing, and without it you really can't characterize a CDR correctly. So unfortunately that's going to be a problem, and this, I believe this supports up to a gigahertz of jitter input. So this is a fairly advanced instrument. Unfortunately, I can't get rid of this. So now the question is, what is going on? Well, the worst case scenario is that someone has put in a voltage outside of the range of the delay control in at some point during the life of this instrument and has destroyed the input, and now the input protection circuitry is just reading constantly a false flag that this input is out of range. That's my guess. I don't think I can fix this with software. I tried for a while, I couldn't get anything. I updated the firmware of the instrument. This is the latest firmware that's on the Keysight's website, so there's not much else I can do about that. So now the question is, what do I do? Well, I think I'm going to have to take a closer look and see if there's a way to remove this and open it and see what's in it. It's both interesting to see the design of this and potentially maybe see if there's a way to fix that. Well, here is the module. This is the generator, pattern generator module. I finally took it out of the instrument. You can see this is how it interfaces to the back of the unit itself. And I actually figured out that the interface of the entire module to the PC is through USB. So it uses a USB connection, which kind of makes sense because each of them plug into a USB port, and then that's how the information is transferred. This also means that, of course, everything is handled on these boards. All the data generation and all the characteristics of the data you're putting out is completely handled in these boards. It has nothing to do with the PC itself, and that also makes sense because there's so much data coming out, of course. Well, these things are ridiculously complicated and made of so many different layers and so many different boards. It's almost a little bit kind of an afterthought in some aspects, and I think that's because back then when they were making these things, they had no choice but to break these into various modules. And the thermal solution in this is just crazy, and I'll show you that. I've taken it apart a little bit to get to the source of the problem. It's interesting to see these thermal parts here where you have channelized aluminum pieces which sit on a module and a fan over here which blows air horizontally across into it, and there are multiples of these stacked up, as you can see, each of them dedicated to a different portion. So in terms of problems, unfortunately, this is becoming a little bit worrying, and I'll tell you why. I'll tell you what my strategy is, and this thing is full of custom ASICs and custom modules from Keysight. Of course, you can see many amplifier modules here in various locations. Interesting thermal design on those heat sinks, which are designed to interface to the PCB. There is nothing connected to them. The PCB itself conducts heat laterally and then onto the heatsink and out, which is a clever little design. I've seen it in other places as well. So what is actually going on here? Well, I took out this module, and this module is what the control delay input in the front right over here is actually connected to. And this doesn't have a lot of interfaces on it, so I want to talk about that a little bit. Now let me tilt this a little bit as well to show you what's going on. So at the top we have the clock generator, and at the bottom we have the actual data generation, and these are connected with GPPO I/O connectors to the front-end amplifiers, and there's multiple stacks of those as well, and they all need to be thermally cooled. These things are quite power hungry. These are basically very fast slew rate, I would imagine quasi-linear output drivers which drive into 50 ohm differential, and this is what you would expect from a backplane driver. Nowadays it's so much more integrated by about a factor of 1,000, so it's really quite incredible. And of course at Bell Labs we build these kind of devices too. So now what do I do with this? Well, let's take a look at see what's going on here on this module. So as the manual also says, if there is an overvoltage condition detected on the delay input, the instrument will disconnect the delay input and will not allow you to inject anything into it anymore, and therefore protects it. But if you look at this board, this is an interface board where the input is, by the way, everything here is extremely EST sensitive. I'm on an EST mat and everything, so you have to be very careful with this. So this module over here, I'm just terminated into 50 ohms right now, no reason, just so that I don't lose the connector. It's got a relay here. You know what? I think this is one of those things where it's probably best if I zoom into it so you can see what I am talking about. There we go. This is probably better. So here's the input. This is a relay. This is a mechanical RF relay that isolates the GPPO connector here from the SMA input. This is an LED, which interestingly enough is not even visible from the front panel. It's blocked by metal, but it is on this module anyway. There's a 3-pin connector which is used to provide ground and energize the relay. So if there is an overload condition detected, it will simply switch this relay. There's a little transistor and a resistor there for the LED. So this itself is most likely not the cause of the problem, because there's really nothing here. Unless somehow the energizing voltage of the relay is leaking into the RF port back into the module, I don't see why this would be the problem. I can test this separately nonetheless just to make sure. So this does make things a little bit worse, unfortunately, and the reason is because I suspect that the problem therefore is with the module itself. So oops, I should have removed that. So if you look over here, this module down here is where this cable goes into. So if the problem, the detection of the overload condition must be happening inside the module, and therefore if the problem is that this is already damaged, we're kind of screwed, because that is done all inside, and that's all completely a custom module. So I don't know what I can do about that. So what are some of the things we can try to make sure that that's not the case, or to isolate the problem further? Well, I'm going to have to put this back in the unit, bring these connectors raw outside of the unit from the front little hole that's there somehow, and basically test them without this front module. and test this front module separately. This will allow me to measure DC voltage at the input of this and see if there is any back voltage coming out indicating a damaged circuit on the input. And that's the first step. Unfortunately, you have to kind of completely close this back up before you can put it, because it's got a railing on each side which is needed to guide it into place. So, and the other thing I also noticed that this thing was filthy, and it still has absolutely tons of dust in it, which means that I'm going to have to remove the other module, the error detector module, and clean that too if I want to extend the life of this instrument. Hopefully we can fix it, or if we can at least do something about the problem we are seeing. Okay, well, here's the new situation. So what I've done is I've put the module back, and I have taken the RF input out to a cable which I can connect to an external source, and I have taken the 3 cables that go into the module and I have connected it to the module itself. It's just sitting here, and right now the LED on it is turned off. So under the current condition, the screen is actually saying that there is an overload condition. So it's detecting an overload when there is a 0 volts applied, nothing's going on. And the screen had to be put upside down like that, so that's the only way to access this. So right now it doesn't work, but look what I can do. If I go ahead over here and apply a positive voltage very carefully and with very little voltage, with current limited into the port. So let's go 0.1, 0.2, 0.3, 0.4 volts. It's drawing 7.5 milliamps into the port itself. This is a really drastic measure. I don't really recommend typically doing this. And I'm going to go to the instrument, and I'm going to go ahead and ask to enable, and guess what happens? The error actually goes away. And as you can see, the LED does turn on, meaning that the port is now enabled. This means that the detection circuitry is working. It's just misfiring when there is no voltage applied. And unfortunately, this can only mean that the input circuit is damaged. Somehow, some ASIC is being pulled towards one supply, and I'm forcing to overwrite that by applying an external voltage. In fact, let me go ahead and turn that off, and you can see as soon as I do that, this thing turns off. But since we're already here, we may as well take it apart and take a look what's going on the inside of it, and perhaps there is something that we can do. Well, here we are into the disassembly, and check out what I found. Now this is a really interesting thing that just came up. Now if you look carefully, you'll see that this top module, which is responsible for the top rows of the SMAs being connected, those are the clocks and triggers and so on, and the bottom module, which is where the data actually goes through and the clock goes through, are identical. They have exactly the same part number. Now here, this port is where the delay control goes in. You can see that's this cable that I have disconnected, which means that perhaps it is possible to swap them. Now, this is a very risky and unusual thing, but it looks to me that they're using the same module to handle these things, perhaps because they require the same kind of performance, the same kind of retiming. They both get clocked from the same kind of place. They both have the same exact ribbon cable connections. You can see the top and the bottom of these ribbons are exactly the same number of IOs are going through them. So could it be that we could just swap them and potentially get this thing to work in one go without having to open this? Because opening these modules is basically impossible. By the way, here it is. Take a look. You can see it's fully enclosed. This is something made by Keysight. This is probably made of retimers and phase shifters and delay lines, and it's made of probably multiple different ASICs. And these things are impossible to find, of course. So let's see what happens. I mean, we are here anyway. Let's swap them and see if the functionality can be restored. And then we'll be using this port here to connect this to, and then maybe this one is fully functional since it's never been connected, and then the port over here on this one is not used, so we just leave it alone anyway, and perhaps it doesn't matter. Okay, well, I swapped one of the modules, and of course thermal paste, new thermal paste is a must because the old ones were all really bad and they weren't covering properly anymore. So we're going to clean all that up, put new ones on, put the fans back on, and continue assembling. Well, surprising enough, the instrument still reports the same error. Even I put it back and I tested it, it does exactly the same thing. It's a little bit different. It doesn't kind of stick, the message doesn't stick around as long. I can sometimes get it to disappear, but very rarely. So something is still going on, unfortunately, which means it has to come back out. And we're going to have to try and see if we can figure anything else out about it. Well, back it goes. Well, I spent a really long time trying to find out at what point inside this circuitry that signal is being essentially miscalculated and misfiring and disconnecting the relay. from the front end, and there is just no way to find out. There's so much stuff in these boards, there's no documentation at all. So I kind of gave up on it. Instead, I came up with a different solution. The main issue is that when this thing triggers that it thinks there's an overload condition, when there isn't, it disconnects the front end relay, that little board that I showed you, and therefore there is no way to drive that port anymore. So I built into it an override switch with a little LED here that shows you whether you're overriding the internal signal and enabling the port regardless of what the software thinks is going on. This way we should be able to at least see if this port is working and be able to take advantage of jitter, introduction of jitter into the eye diagram manually by using this switch. And I just wired it all up and I closed it all up nicely as if it was kind of part of the instrument to begin with. So let's go ahead and put that back together and actually see if this thing works at all and get any data out of it and see if the jitter port works. And maybe there's a way to disable this whole thing in software by hacking the firmware somehow, but we can worry about it at some other time. Let's just get this thing back together. Well, here we are back up and running again, and as you can see, this error of course is still there because that is being generated internally. Now even when I say disable, it's still going to get triggered because the hardware somehow has an interrupt line that's constantly being triggered internally. So obviously it doesn't know how to disable that. Even when I say disable and the relay is disconnected, it still gives me that error. So obviously there's no difference between enable and disable in this case because it's always in disable mode. Now what I can do is I can take this and put it over here. Just put it out of sight and out of mind, and even though it is still there, it doesn't really affect doing anything else with the software. And I have an override button right here. I can go pop, and now it has an override, the relay is enabled, and I can inject my own signal into it, and we can test to see if that works. So other than that, the software looks good. So the next step is to actually connect the outputs to an oscilloscope and see if we see anything coming out of it. We can check the clock, we can check the trigger, we can check all the signals to make sure they're actually coming out. And then ultimate test would be to do a loop into the error detector and to see if the error detector can lock onto it. It has its own CDR, it can run into CDR mode. So there's lots of interesting things we can try out now that we have it up and running. So here's the first setup. It's really quite simple. I'm taking the data and data bar outputs, converting them to SMA. These SMA cables obviously going to have their own little limitations, but I don't have V cables that are this long. Not that it should be really necessary for 13 gigabit per second. And then we have the trigger output here, which I can program to be, clock divided by 2, 4, 8, or whatever I want. And that can allow us to do a nice trigger on the oscilloscope and produce eye diagrams. And we can use many scopes, of course, and I'm going to be using the Keysight S series here because it's nice and close by. And let's go and see what comes out of it. So I can program this into basically any data rate, and we can try a couple of them and take a look at the quality of the signal coming out, the amplitude, and everything else to make sure that it is functional. Okay, here we can see channel 1 and channel 2 of the oscilloscope connected to data bar output of the BERT, and we're seeing a reasonably nice data pattern coming in. This is a differential signal, of course, between the two channels, and it's sometimes nice to look at the signal single-ended because some of the imperfections that will be masked in the differential output can be revealed here. And we can see that there is certainly some ripple. There's the lower side, the low value of the eye is not as good as the high values. There are some extra humps at the bottom. We'll see that when we're looking at the eye diagram. So the eyes are reasonable, but they're not perfect when we're looking at them single-ended. Now we can make this, of course, a differential signal. That's easy to do, but first let's change our trigger because I'm using the other channel, channel 2, to trigger onto clock divide by 8. So here we go, that's channel 2. We can do another rising edge, and that way now we can see something that resembles more of an eye diagram. And more importantly, we are going to have the jitter on the two channels with respect to channel 2 trigger output, no longer with respect to each other. And that's really important because if you start triggering on the wrong channel, actually your entire jitter measurement is incorrect. So this is a nice, you can see zero crossing is reasonable. Let's go ahead and make this a differential signal. There it is. That's a differential signal. As you can see, now it looks a lot more symmetric, of course, but that's the nature of a differential signal. The wander and DC offset and ripple on the common mode channel, which is now shown in blue, is okay. I can live with that for an instrument that's, I don't know how many, 15 years old or so. Okay, let's go ahead and remove this channel. I don't really care about common mode. Just look at it. Oops, that's not what I wanted to do. I wanted to turn this one off. Okay, so I'm looking at the mouse through the PC and it's a bit of a lag there. Okay, there it is, looks nice. Now we can create an eye diagram out of this, and there's a functionality built into the scope for that. That's pretty easy. We can just do a quick eye diagram, and there it is. The instrument does that. I don't know why it creates such a big window at the bottom. That's silly. There it is. That's a fairly nice looking eye. Now,
Obviously, this is, we don't know the data rate actually. You know what? Let me just show you the data rate first. That's going to be important. We can add that measurement very simply. Let's go through data. There's a lot of stuff we can look at, but data rate is the simple one. There it is. Let's apply that. We're looking at about 4.25 gigabit per second. That's the mean value, and that's exactly correct. That's what the BERT is set to. It's set to generate 2 to the 15 minus 1 Prbs sequence at 4.25 gigabit per second. It's some standard. It doesn't really matter what it is. The data is a Prbs sequence. And the eye diagram differentially looks nice. It's very symmetric. It's got nice opening, very, very wide opening. It has reasonably good jitter, of course. And there is no channel in here, so I don't expect to see much ISI. I only have the connector and the cable and the scope itself. At 4.25 gigabit per second, for a scope that has 8.4 gigahertz of analog bandwidth, you should have no problem with ISI at all. So this is kind of the raw eye we're getting out of the instrument itself. And it works, and it looks quite nice. We can change the data rate, of course. We can go to a higher data rate and then compare the eye. And well, check this out. This is now an eye diagram running at 10 gigabit per second. You can see the mean value down here is 10 gigabit per second, and the eye has a much more sinusoidal shape to it, and that's to be expected. There's quite a bit more frequency content here. We're beginning to see ISI appearing on the eye crossing, as to be expected as well. At 10 gigabit per second, we're actually starting to push against the bandwidth of this scope itself. Even though half the baud rate bandwidth is only 5 gigahertz, there's still frequency content above that, and of course it's going to be affected by the brick wall filter of the oscilloscope itself. Not so much, but certainly some of this, a little bit of this, is going to be the consequence. Oh, that was interesting. Look at that. Something happened. Yeah, there was some weird event happened where some cycle was slipped, and you can see it generated a lot. That's interesting. Well, we're going to find out if that's a problem or not. Let's clear that and do it again. That was a little bit unusual. I wonder if that was from the scope or from the BERT itself. So you can see how little it takes to generate error. What you just saw was tens of millions of errors, because as soon as you have some problem like that, you're generating many, many errors in a row, a burst of them before the system locks again. Now this could have been because of a trigger point of view. Let me go ahead and turn on channel 2 so we can take a look at our trigger. This mouse is really slow. Let's see, there's our trigger signal. It should be there. Looks okay. Maybe the reason is because, there you go, that's our trigger. It looks reasonably good. I don't think that's a problem. Let's turn it back off so the eye diagram doesn't get messed up. There you go. So the trigger signal was certainly there. It was drawing the eye diagram of the trigger on top of everything, and of course that's going to mess everything up. But it looks very good. So I know that the signal is being generated, and that's very important. And now we need to find out if that jitter port is actually working or not. And the easiest way to find out is to add some signal into it at a much lower baud rate where the jitter is completely clean, because there's no ISI, there's nothing. You're going to get a nice eye crossing, and then we can see if our own jitter switch that I added is working at all.
So here's our setup to look at the jitter on the eye diagram by introducing jitter ourselves. And I'm using the Tektronix AFG 31000 series in order to introduce a 100 megahertz square wave directly into the delay control line input, which I can enable and disable with the switch that I have installed here. So this means that I'm going to apply a 100 megahertz jitter into the eye diagram. That's the jitter composition. So that means the eye is going to move back and forth at the rate of 100 megahertz and with fixed amplitude. So it's going to jump between two separate positions. So it's going to have the highest histogram distribution presence at the extreme edges of those 2 points. Now this thing can do up to a gigahertz of jitter frequency, and it can do it up to plus or minus 200 picoseconds. So it's quite a lot, and we should be able to easily see that even at low data rates, even less than a gigabit per second.
So here is our eye diagram without any jitter. This is at 1.25 gigabit per second. So you can see it's very nice and really, really open. It has almost no ISI on it and has its own intrinsic random jitter and perhaps some data dependent jitter, but not so much of it. So there is nothing being applied. I'm going to go ahead and flip the switch, and let's see what happens to the eye diagram. There it is. I flip the switch and check it out. We're going to have to clear the screen so we get rid of the distribution here and see it once again. There it is. And what do we expect to see? Well, we expect to see 2 distinct edges, and that's exactly what we see. You can see that we have some crossings that are bunched up over here and some crossings that are bunched up over here. This is of course a color coded eye diagram, meaning that the brighter the colors are, closer to white, the more the eye spends, the crossing time spends at that position. So this is normal to expect, and in between you're going to have the transitions as the finite rise and fall time and finite jitter bandwidth that we have from the system. But you can clearly see that the jitter can be applied to the signal, and this is a very useful tool to stress clock and data recovery systems to see how they react to when they have a particular jitter composition. You don't have to put a square wave, of course, you can put any waveform you want, and that's going to be directly translated to the jitter frequency content. So that part works. I think at this point we should go back to the instrument and see if the error detector works, because a lot of the functions of the transmitter seems to be working just fine.
And here I'm going to test the error detector. I'm connecting the two outputs of the pattern generator directly to the two inputs of the error detector. I'm also bringing one of the clocks into the clock input of the error detector. The clock is not necessary. This thing does have a CDR, but it's not continuous rate. So there are some gaps in the frequencies it can lock to, and for whatever it cannot lock to, we're going to use the clock as the loop over. So other than that, it looks good. Let's go try it out. So let's go ahead and try the error detector here. So I have the pattern generator to set to 500 millivolt I, that's reasonable. And let's go for a fairly high bit rate here. Let's see what I have here in the list. Let's try just 10 gigabit per second, which is the maximum roughly of what the clock and data recovery of the receiver can do. Now we go under the error detector here. Sampling point, we're going to have to try that once we get the I actually. So I can go ahead. I use an external clock, or I can use the clock and data recovery. Now the external clock is going to test whether the clock output is working, and obviously the CDR is going to test the CDR. Let's go with an external clock and check it out. There it is, BER is 0. So with the external clock, of course, everything gets locked in automatically. And if I go to the here and if I go auto align here, it should give me a nice looking eye diagram. There it is, that's reasonable, not too bad. You can see we have obviously some jitter, 85 picosecond eye opening. And we can go and do a whole bunch of different analysis on this. We can do timing analysis, and we can see a bathtub curve. That looks okay. We can go ahead and see the output level. Similarly, a similar type of bathtub curve, but for the vertical, and also looks good. It's reasonably symmetric. You can see 225 millivolt here and about 250 millivolt at the bottom. Nice symmetric eye. And we can do an eye opening test. Do this because this thing has an eye monitor, and here's our eye opening. You can see that we have obviously the red regions are representing of a particular bit error rate. So the red regions here are basically bit error rate of 1, and the black region is bit error rate of 1 times 10 to the minus 7, which is quite good. Basically it's error free essentially. And we can go ahead under the result menu, see the bit error rate here. We can look at the accumulated results. We can look at the eye diagram that we get. So it seems to be working really nicely, and this is of course in local loopback. Now the other thing I want to try out to see if the CDR works, we're going to put this into clock and data recovery mode, and I'm going to put my own data rate here. Actually, I'm going to have to change that to this one. There it is, 10 gigabit per second. I have that here in the list, and check it out, it also logs with its own clock and data recovery, and it should have a similar performance. We're going to auto align this one as well. It should be just as good. There you go, there you go. It's even a little bit better actually. So looks very good. Now of course with clock and data recovery you're going to have a different jitter characteristic and all that. We're not going to get into the details of that, but it works quite nicely. I can go ahead and do another eye monitor analysis here. Looks good. There you go. Nice, beautiful eye, dead center, because it's done an auto alignment. So it actually works really well. It's a shame that that little delay control input has an issue, but as you can see, I can overwrite that. So it is essentially completely functional. Now, having said that, this is just a loop back. We should at least put it through some kind of a backplane channel so I can show you that indeed you can do analysis of ISI directly on the instrument. Just to show you what happens when you pass this data over a backplane, here I have a Xilinx backplane emulator. This is a 10-inch trace here that I'm passing the signal through, but just to stress the instrument more, we're going to use single-ended. So I'm terminating one of the inputs and one of the outputs. We're only looking at a single-ended data going through the back channel. That makes things, of course, quite a bit harder for the instrument. But it's the same rate, 10 gigabit per second, 10-inch copper. Let's see what happens. So to partially compensate for the fact that the data is single-ended, I've doubled the signal amplitude to 1 volt peak to peak. So now if it's of course the same data rate again, 10 gigabit per second, nothing's changed. But now if you look over the error detector here, if I auto align it, you can see how much closer the eye diagram is to being completely basically destroyed by ISI. And as you can see, the opening is now tiny. It's only 100 millivolt. We have significantly less margin both on the vertical and horizontal eye opening. In fact, if I go and perform a bathtub curve, so this was with just a feed through with no channel, and with the channel, of course, you can see significantly narrower, and this is going to be the same thing for the vertical as well. We're going to have much smaller. Look how small for the bit error rate threshold of 1 × 10⁻⁶, how little there is left, and that's to be expected. And on the eye monitor, I'm going to run this one more time, and we can see, yep, we have quite a bit smaller eye opening. So the instrument is very nice, it works, and if you have some ideas on how to modify the software to get rid of that ridiculous error that it gives you, that would be fantastic. But again, thanks to my Patreon supporters, I can get instruments like this and show you what it can do. Now that we have this bit error rate tester here, this is going to be one of the instruments that we'll use to test other equipment with different kinds of oscilloscopes and software packages that come with them. We're going to be able to use the BERT to test them. So these are very valuable for our future experiments. And I hope that you enjoyed this video. Let me know what you think about the comment section, or if you have any other ideas on how to proceed with this instrument. As always, I'll see you in the comment section.